So this lesson is what we've been building towards with our other calculator lessons. So in this lesson, I'm assuming that you've already done the lessons on the n derivative function on your calculator and the fn int function on your calculator. So this finds derivatives, and then this obviously finds integrals. So I'm assuming now that you know how to do that. So if you've not completed those lessons, go back and do that first before you tackle this one. In this one, what we're doing is we're using these functions to tackle problems in context. So this is actually the way that a lot of people who work in sort of applied math fields do math, right? So a lot of times if you're an engineer or you're in the sciences and you're dealing with statistical models, your computer spits out a function, and here's an example that we're going to look at here in a second. Your computer spits out a function that models a certain phenomenon, and it's usually not a very nice function, but the computer can also evaluate the derivative for you, evaluate the function or the integral or whatever you need. Where you are smarter than the computer is figuring out how to interpret these problems and figuring out what function that you need. Okay, so that's really what this lesson is about, is figuring out how to interpret your answers and figuring out how to ask the calculator for what you need it for. So I'll show you how to do this one. This one is pretty straightforward, but as we'll see, the interpretation piece gets a little bit harder depending on the type of question you get. So this says that this function d represents the rate at which the depth of the snow on the ground is changing in centimeters per week. And we want d prime of 3. So we want the derivative of d at t equals 3. So I've typed this into my calculator using the n derivative function. And you can trust me that I've done this correctly. Should look about like this, right? With d dx, the function, and then, and then x equals 3. So I'm going to evaluate it, and I get negative 1.018. So that's my solution. So d prime of 3 is this result here. I'm around to 3 decimal places because that's what we're going to do in the AP exam. So d prime of 3 equals negative 1.01. So that's our result. Okay? And then you're going to have to indicate units of measure. And that's where things get a little bit trickier. So if d of t, remember it told us, is the rate of change in centimeters per week. So it's already a derivative if you think about it. D prime of 3, well, that's the rate of change of the rate of change. So this is going to be centimeters per week, or centimeters per week squared. So this means that the rate of change is decreasing at a rate of about 1 centimeter per week. So this one was pretty easy except for the units here, and for that we needed to just recognize that my original units were centimeters per week, so my derivative is going to be centimeters per week squared. On Delta Math, when you give a solution, and when you get one wrong actually, it gives you the explanation and the picture of the graph. I think this is super useful, and as you do these, I encourage you to read these every time, whether you get them right or wrong. So knowing that this derivative is the slope of the tangent line, and explaining how this relates to the context of the problem are things that you're going to need to do in the AP exam. So this is super worth your while to just read this, especially when you miss them. We're going to move on to some harder ones here in a second. Now's a good time to pause and just make sure you can kind of reproduce my result and you understand why I picked the units that I did. So here's another example. This is really similar to the last one, right? The rate at which the depth of snow on the ground is changing is our function z of t. Units are a little bit different. It's pretty much the same thing. Determine the value of the integral from 0 to 8 of z prime of t dt. Okay. Remember, the integral and the derivative are opposites. We're going from 0 to 8. So the way we evaluate this integral is really just going to be z of t evaluated from 0 to 8, which is z of 8 minus z of 0. Okay, So here actually we don't need to take an integral or a derivative, we just need to recognize that it's asking for us to evaluate the function. So there's a couple different ways you can tackle this on your calculator. I think the most efficient way is to type in the function in your grapher, so under y equals, and then do second calc, value, and it'll take a second to graph it, and of course we're going to get some kind of wavy thing because we're looking at a sine function, right? And then we'll say x equals 8, and we'll make a note of that value. We'll keep an extra decimal place because this is a intermediate value, so we'll keep 4. 4982, and then it's a 0 after that. 4982 is z of 8, right? Minus z of 0, so we'll do 0, and you can just hit 0. You don't have to do second calc again. And it's y equals 0. Okay. So this integral is just equal to 2.498. We'll round to 3 decimal places now. And these are values of the original function, so this is going to be inches per hour. And why will we do this? Well, here it's useful to look at the interpretation. So here's the graph, and here's our integral. So notice we went from 0 to 2.498. This integral is the total change, so it's the sum of all of the changes. So the derivative is change, and the integral is a sum. That's why it's kind of this curly S boy, right? S for sum. This integral is the total change from 0 to 8 in the rate of, what was it again? When we were talking about snow, right? The total change in the rate at which the depth of the snow is changing. Okay, that's kind of a mouthful. Okay, but that's our interpretation there, and that's why our units match our original function. Again, look at this interpretation every time as you do these. It's super, super valuable. Okay, this is going to be the last example in this part of the video. This is going to be a two-parter because I want you to see all the types of problems you might run into. But here, this is an initial value problem. So it gives us n of t, and n is the rate at which people are entering a sports arena. It's good to annotate what the functions are, by the way. In people per minute, it's also good to annotate the units. And then it gives us time t equals 0, 170 people inside the arena. We want to know time t equals 25. Okay, so if n is the rate at which the people are entering, we need to integrate to get back to the number of people in the stadium, right? So n you can think of as already the derivative of the number of people in the stadium, and the integral of that is going to give us the total change. Okay, so we want to write an integral, and it's going to be the integral from, we want from 0 to 25 of n of t. And you can solve that on your calculator. So I've typed in my whole function. I'm using the fn int, right? The integral from 0 to 25. Used x as my variable, and then I said dx as my integral operator here. I'll let my calculator figure that out. So this is my result. So that means 414,000 people is the total change in the number of people in the arena from 0 to 25. Okay, let's make a note of that actually. So this integral, and we're going to come back to the number in a second, is the total change. Okay, so this integral represents the total change in people from 0 to 25. We want the total number of people from 0 to 25. So it's going to, the total number of people is going to be the total change in people plus the number of people that we started with. So plus that 170 people, and that's people at t equals 0. Okay, so on my calculator, I'm just going to do plus 170. And that is my result. So 414,980, and it says to round to the nearest whole people, which makes sense. So we'd say 414,980 people, and that would be my answer here. Okay. So remember, this is called an initial value problem. So we want to do the total change plus that initial value.